Hi again. So, basically, we're in part 2 of the geometric probability series. I think right now would probably be a great time to define exactly what geometric probability is. It's essentially a tool or a system of tools we use to deal with probabilities when there are infinite outcomes that are also bad, quote unquote, and good, quote unquote, as opposed to a system where there's a discrete or finite amount of outcomes, like a coin flip or a dice roll. For example, our last video, which I highly recommend you watch, link will be in the description, tackled Buffon's needle. And we found that representing our problem in a geometric space was useful because there was infinite possibilities of dropping our ruler. We're going to look at these techniques and understand when to use them, how to use them, and later, what geometric probability says about probability and math in general. We learn math through problems, so let's start with the problem. What is the probability of landing on the left side of this line as opposed to the right side? Well, if the left side is equal to the right side, that is obviously 1/2. That's clear. However, let's think of a different problem. What if I had to go to a meeting at 12:35 and it was equally likely I would arrive anytime between 12:30 and 12:40? What is the probability I would arrive on time or early? Well, that's also obviously 1/2. But what if we draw a line from 12:30 to 12:40 and draw 12:35 in the middle? Well, now we're really just solving the same problem as we did before. You might say, hey, well, Anu, I didn't need a timeline to figure that out. Well, of course you did. The core idea of translating a probability problem to a timeline or a number line is associating probability with length. Well, if we can associate probability with length, we can associate probability with area like we did last time, or maybe even probability with volume and hypervolume and higher dimensional things. Let's deal with a little bit of more higher dimensions. Lines are kind of boring. No offense to any lines watching. So, what is the probability of having two numbers, both of which are smaller than 1, where the sum of their squares is also less than 1? Okay, let's think about that. Now, we could work out the probability of that, but there's an infinite amount of pairs of real numbers that fit our conditions, and also an infinite amount that fit our first conditions and don't fit our second. But this is a sure sign that we need to use geometric probability to find out our answer. Since we're dealing with a pair of numbers, as opposed to just one time variable in the problem before this, we're going to be working in 2D, not 1D. Now, let's think about this. We want to think of a shape that represents our first condition, a shape that represents all x and y coordinates between 0 and 1. Let's think about this. Okay, so that's pretty clearly a square. Now let's think about our second condition. What shape represents all coordinates where the sum of the squares of x and y is less than 1? That's a circle with radius 1. So we're looking at the square, and our question is essentially asking, what probability is there of a point inside the square also being inside this quarter circle? Well, that's really just a question of areas. What is the ratio of the quarter circle's area to the total square's area? Which is relatively easy to compute. It's just pi over 4. So we're going to do one more problem to prepare ourselves for more challenging problems in later videos. So, say we have me and my friend Josh. We're going to meet up at a pizza place. And we're very not organized. So we each come to the pizza place at a random time between 5 and 8 p.m. We will each wait for each other for 30 minutes before we leave. What is the probability that we meet each other? This problem isn't as straightforward as the others, but since we're dealing with infinite outcomes and infinite also successful outcomes, it'd also be a good time to use geometric probability techniques. For our problem, just for ease of writing, let's define 5 o'clock as time 0 and define 8 o'clock as time 3, as it's, 3 hours later. So by that definition, we will each wait for a 0.5 amount of time. It is also worth noting that it really doesn't matter who comes first, as we're both waiting for the same amount of time. Like the last problem, we're dealing with two variables, when I come in and when Josh comes in. Let's say the time that I come in lies on the x-axis and the time that Josh comes in lies on the y-axis. So let's imagine I come in at time 0 and Josh comes in at time 2. We will clearly not meet since I can only wait for 0.5 hours or 30 minutes. Instead, let's imagine that he comes in at time 1.5 and I come in at time 1.6. We will clearly meet as Josh will have waited 0.1 hours. Now, so what we're looking for is all of the pairs of numbers that are 0.5 hours apart. So at maximum, we are looking at x plus 0.5 equals y, and x minus 0.5 equals y. Now, if you think about these equations should make sense, as y is Josh's arrival time and x is my arrival time. These are our bounds for our successful possibilities. So now we have this diagonal-like shape. It isn't really easy for us to calculate the area of the shape directly, but maybe we can calculate the complement, or the part of the graph that isn't within this green portion. Now, the area of the triangles together is 6.25, and since our total area is 9, as 3 times 3 is 9, our strip has an area of 2.75. And if we divide the successful area, or the area in which we meet, by the total area, 9, the probability we have of meeting is 11 over 36. Josh and I should really nail down our timing. We're basically never going to meet. Regardless, all this talk about pizza is really making me hungry. Many of the problems that we worked through today were from Brilliant's article on geometric probability. Brilliant is a great website with tons of problems and lessons that have everything from number theory and geometry to computational biology and AI. I swear I'm not sponsored, but could be sponsored? Thanks so much for watching. As the best learning happens when you figure it out for yourself, I want you, the viewer, to think about what happens when Josh and I wait for different amounts of time. Think about that while I labor away on the next video on the series where I write super fast again. If you don't want to miss that video, I'd click the subscribe button, but that's just me. Alright, thanks so much for watching, and I'll see you next time.